Instrumentation and control systems. This is a hints and tips video. What we're going to be looking at is the first learning outcome 1 for this unit, and there will be sections of this video. This will help you with your assignment, but please note you need to make sure that you use the UniCourse guide notes and further reading. I'll explain this more to you as we're going through this presentation. So this learning outcome looks at identifying instrumentation systems and devices used in process control. What do I mean by that? Well, if we take a system like a conveyor system, even so it uses a PLC. The system also has to measure the pressure, sometimes the temperature, how many times things are moving along the production line, and this all needs to be fed via signals. So we'll be looking at all this in a bit more detail. Now, instrumentation and control is a measurement automation. So we can use multimeters, lots of other devices, but we use this more in a very more sophisticated type of way. And we're looking at instrumentation and control and see how we can use it and the process of it as well. It's also important because we are using these in an industrial setting. Safe control is very, very important so that nobody is harmed and systems are running correctly, effectively, efficiently and things like that. This is where we have to make sure these systems are all being monitored correctly. Now, of course, all this instrumentation will have their own sort of signal terminology, so it's important that we understand this. We understand what signal conversion is and conditioning is, process control, terminology, system terminology and the concepts, and also tuning. And we'll look at these different parts throughout this presentation and other presentations we're looking at for the part of Unit 16. Now, to get these systems monitoring, we have to use sensors and transducers. We'll look at these in a bit more detail, and these play a key part on the instrumentation. And we have things like a resistive, inductive, capacitive, ultrasonic, pressure and semiconductors and thermocouple and optical devices, and these all can detect something or measure it as something that needs to be changed, that we need to then manage in the system. Now, instrumentation signal terminology. Now, this is including the accuracy, the error, the drift, repeatability, linearity, sensitivity, resolution, and all these are very important when they're part of the system and how it all operates and the terminology we use. Now, when a signal comes in from the outside world, it just doesn't come in there and stay like that. It has to be converted. So we have a thing called signal conversion and conditioning. Now, this can be a very simple where we have an analog and that's converted digital or optical, and then we can connect that up, and we also use a microprocessor to manage it, or a wireless system, and also of course we have industrial standard signal ranges. That's important because if we don't have that, then these devices won't operate. So firstly we're going to look at is sensors and transducers and how they're used in instrumentation. As I mentioned before, we'll look at resistive, inductive, capacitive, ultrasonic, pressure and semiconductor, and of course thermocouple and optical. A transducer is this generic word which is used there for components that convert a variation, and it's converted there. It will take this in and it will then allow that to be transduced or converted into a signal which can be used within the system. And here is an example of one. What we've got here is a device there that will pick up, detect the signal. We've got the pulse there, which will be then used as part of the display, and then we've got a signal which is converted into a digital output through here, and then we can use it on the 7-segment display. And we're going to be looking at something like this in a simulation later on. Now we also call this a data acquisition. We're acquisitioning the data from a signal, and that converted, and then it's going to be used and managed within the microcontroller. And here we have an example of the transducer here, where we've got the signal here, which is a microphone, and that converts it from the pressure in the microphone, from the sound of a voice, and that's converted into electrical energy. That's amplified, and that is another electrical energy signal, which is then fed into a loudspeaker, which then converts it back into a mechanical energy. And here we have the loudspeaker. We can see here the diaphragms here inside there, and we've just seen this in the previous one, where we convert the mechanical energy, electrical energy is amplified back into mechanical, and then we can hear it as an audio signal. Now we need control systems, and here's what you use in the domestic world of fridges, the temperature, the mobile phone, brightness controls are set on the screen, phone charger so it doesn't have a high voltage to actually blow the phone up, and street lights, of course, where the light will operate it so that in the daytime that will be a time when the lights will go out. So continue on signal terminology used in process control. We're going to look at some of the other terminology, and the first one we have is impulse response, and this is where the word impulse is that we do get a brief input signal. Sometimes things do change, and we just get one signal on the input, and that has to be monitored, and then it has to be managed. Now the frequency response, this is a quantitative measure. Now quite often we have this in things like we're measuring the frequency response of audio amplifiers, but sometimes where we need to use signals of a wide range of frequencies, it's important that the detector can actually detect a wide range of frequencies, especially when it's an AC signal. Now the resolution, now this is where we're looking at how the equipment that's measuring it, monitoring it, managing it can actually be seen. So for example, in resolution used on things like the multimeters or devices where we want to measure it. So sometimes we need to measure a very small amount of current or voltage or temperature or sound, and it's important that the resolution is manageable enough so the operative can actually see it. And of course sensitivity, this is where an input to a device and the fact that the actual device can pick up something. Now if we're actually measuring things like voltage or current, we may need to go down to things like microvolts or milliamps, so it's actually sensitive enough to pick up these signals. Transfer function, this is where we actually move one signal to another and the ratio of the output quantity to the input system, and we may sometimes use that with the efficiency of it as well. So this is an important part of the system. Now the stability, now if you've got a device which has to run at a certain speed or a certain temperature or something else which needs to be kept constant, the stability is very important, and this is where we have feedback loops keeping and monitoring and managing the system so it is kept at the right temperature, the right level of sound or heat or liquid quantity of stuff like that, so long as it's kept stable. Now noise. Now this is something which is probably a lot easier to manage. A lot of the equipment we use today will have things like Faraday shield, or the cables were screened, because anything that's sort of not part of this main signal, whereas a pulse or some form of interference can affect the signal, which can then affect how the system is actually managed. Now the signal to noise ratio, now quite often we need to make sure that the cabling we use or the devices, that the signal is a lot larger than the actual noise level. In other words, if the area where we're working in has a high level of noise, the signal has to be well above it, and we call this the SNR, the signal to noise ratio. A dynamic range is sometimes can be known as a frequency response. So the dynamic range is the actual fact where describes the ratio between the smallest and the largest signal. So this sometimes we are measuring from things like a microvolt up to voltage. So you put in there, say 10 millivolts to 10 volts, and that would be the dynamic range. The linearity of it, this is where everything works in a linear way and it doesn't just jump up. So you go from 1 to 2 to 3 to 4, not 1 to 3 to 5 to 7. It goes in that formative way. Now, there's many types of transducers, depending what the industrial setting and what it's being used for. This is where we'd have to look at them and see how they're used and how they control and processed. Simple temperature sensor on the thermometer, usual one, the one there, we can see that, very simple one. And here is this handheld electronic one which is used these days to measure the temperature of a human being. We have optic sensors, and they will detect light and they'll put the lumens inside. We have also used an optical sensor. There's a photovoltaic sensor, semiconductors and stuff like that, and thermoelectric optic sensors. Here we have one here. So what we've got there is we have this which is coming is known as the beam, which comes out here, and that is reflected back here. Now if you break that beam, it's saying something's happening. We'll send a signal back to the management equipment saying switch off or switch up or higher the temperature, whatever else. This is what you've got, this beam here and the reflector there which sends it back. And there is a typical sensor there, photovoltaic type of sensor here. Usually we'll have two LEDs, one transmitting it out and the signal then be fed back into it and it's broken. There's like that there has been a signal disruption and that has to be managed in such a way. Known as a photoelectric sensor. We have resistive sensors. Now we'll see here what we have here. We have this thermistor, and that thermistor is then will change when the heat is applied to it. So you have some form of flame, and that is near the thermistor. That resistance will change, so the voltage ratio of these two resistors here will change, so the voltage output here will change. So once it goes back to a sort of norm, it will go back to its original voltage. As soon as you apply here, the resistance will change, which will allow this volt drop across R2 to change as well. Now we have inductive sensors. Quite often they will use where we've got electromagnetic, when we're measuring devices where it's affected by the magnetic field. And what usually happens here is that the inductor will then sense it and it will then send a signal back to the management systems. So here we have the diagram of the inductive sensor, and what we know it's inductive is because we've got this coil here and we have this magnetic field. So as soon as we put something that's affected by a magnetic field, it will then change the voltage, which goes back, sends a signal back to it. So that's the inductive sensor. A capacitive sensor. Now here we're going to be using it. Let's look at the diagram here. We're using some form of capacitor effect here to detect liquids or solids, and it's normally used through non-metallic tanks or vessels. Here is the actual diagram of one here. This is how they are housed and how they work. By putting the device in front of it, and they'll detect it and send a signal back to the management system. So the components are the housing, various shapes and sizes, the basic elements of it, depending on the technology, the electronics to evaluate the sensors, and the connection to provide the power signals. This is what the basic part of it is. Like an inductive valve, you need a signal of some description to go back to the management system. Pressure sensors. Now these have been around a long time. They have been originally used in alarm systems. We used to have pressure mats, usually where it will convert, and this is where the transducer effect comes into it. And we can see where they use the pressure here. And this is using like a silo or liquid, where the liquid reaches a certain level, either high or low. It then is detected, send a message back through the USB, back into the computer saying switch it off, switch it on, depending on the level. And that's used as a pressure sensor. And here's another device here showing you on how that's connected up as well. We briefly mentioned the thermocouple. Let's go into a bit more detail. And what we're looking at here with the thermocouple is that we've got two dissimilar metals connected together, usually wrapped around each other. By applying some heat to it, we can actually change what is known as a voltage to it. And we can see here how the thermocouple is used in this sort of system here to monitor the actual temperature there on an industrial site. So it does measure a wide range of temperatures, but it converts it into a small voltage, quite often not in millivolts. Now, the signal that is converted usually is an analog signal, so we need to be able to convert that so we can see that on a digital display. And this is where we use a thing called an A to digital converter, ADC. And then if we want to repeat or reverse the process, we then convert it back to a DAC, which is digital to analog conversion. And here we have just diagrams showing here where we're looking at this as simulation in the next slide, where we actually put in a digital signal and we can look at the actual analog output. And here we have where we apply an analog signal into an ADC, and there we have pulses, which is the digital signal coming out of the output. Now, what we're looking at here is an analog to digital converter. Even so, we've got the electronics around it and we've got a logic circuit. I just want to sort of take you through what the signal's doing here. So what we've got here, we've got a 5 volt 100 hertz, and we can see on this graph where we've got this AC signal. Now this signal is being fed through these circuitry here, and these logic gates here. These are NOT gates and exclusive OR gates. But what's happening here is that when we actually apply the signal, what will happen is certain things will change. So let me just stop it and let me just start it again. And as you can see here is that when we apply it, we're getting here on the output, these are binaries, so it's basically going quite fast. She's counting up 1, and when you got 2 on, you got 3, 4, 5, etc. And of course we can see the output here on this logic analyzer. So what we have here, this is what is known as an analog to digital converting the analog signal into a digital output. So we're going to look at a circuit simulation. This one's going to be a digital to analog conversion. So before we put the simulator on, let's see what's happening. We've got this basically 3-bit, but there's actually 4 input signals. So if we feed either a 0 or a 1 into each one of these at different times, this will then be converted here through these 2 op amps to this voltage output. So let's switch on the simulator. Let's start with the first one here. You've got 18 point. Now if we just switch these all off, and we're starting off with a minus 3.86 millivolts. Now as we are applying a voltage to it, or should we say a pulse to each one of these, the voltage will go up. So we go up again, we can see it 7.5, up to 3, and then up to 4, and that was it. So this is converting the digital signal on this here, on the input, into an analog signal on the output there. Thank you. Now this is an important part of this presentation. Industrial standard signal ranges. Hint, hint, possibly on your assignments. Remember all this, look at this in a bit more detail. Now what we're looking at here is that the signal that actually is going through the systems, we can't just have any old signal. This has to be at a certain a current range usually around 4 to 20 milliamps, which is the DC standard. Okay, quite often it's 4 milliamps, and that represents 0% of the scale, to 20 milliamps, which is 100% of the scale. Usually with what we do have is voltage, and when we apply the voltage through the resistor we'll get some current. So the percentage is between 0 and 100%. So here we have it here, an example of 420 milliamp, which is a standard analog signal, and we can see that's through a thermocouple through here. That's applied through that resistor, which has a volt drop, and there we can see the analog meter there measuring it there, and that's measured temperature in degrees. Now, hints and tips in completing this assignment, and this is what we need to be careful about. Use the UniCourse workbooks as your starting point. Further research is important. Look at the assignment questions carefully. Don't take it on the first reading. Look at it a few times. Make some notes. Draft out the evidence and put some information together before you actually type it all up. And don't forget to use Harvard referencing to identify where you found the research evidence. Most importantly is any sketches, diagrams, graphics, images that you put within the assignments which you have downloaded from the internet. Make sure you reference it all. And importantly is, instead of listing direct text, which we can check with our systems, rewrite it where possible and include referencing as well. Make sure that your diagrams, as you can see here, are well annotated. Use your own words, and also include any associated diagrams like waveforms, things like that, and you can include letters or numbers and then identify each one. And of course, don't forget your Harvard referencing, and here's an example of one, but also include referencing with all the diagrams, schematics, graphics within the assignment. Thank you very much.
There we go.